folks. In the second part of this video, I've got a handful of example functions here. I've called them f, g, and h. And they're three relatively simple functions. We're going to use these as our crash test dummies to see if we understand these concepts. So we're going to make some new functions out of these by using these as the base for our operations. So just like I did 4 plus 6 is 10, I'm going to do f plus g equals, well, it's going to be f plus g. So let's take a look at this function. Let's say that I wanted to know what was, first let's talk about evaluating. So these are the three things we're going to do. We're going to evaluate, we're going to make formulas, and we're going to find domains. So for evaluating, the kinds of things I'll ask you to do are just say, hey, what is f plus g of 6? And the answer is, well, that's f of 6 plus g of 6. Now I know f of 6 is 2 times 6, and I know g of 6 is, well, let's see, that'll be 6 squared minus 4 times 6 now, won't it? Because I just put 6 in here everywhere that x was. So here's f of 6, here's g of 6, and now we just need to finish evaluating. This thing right here is 12. This is 36 minus 24. Well, that also happens to be 12. So my final answer is 24. So f of 6 was 12, g of 6 was 12. So f plus g of 6 was 12 plus 12, which is 24. Same thing if I asked you to find g times f of 1. That would be g of 1 times f of 1. So I'm just going to multiply them together at that point. So let's see, g of 1, it's 1 squared minus 4 times 1. So that's negative 3. F of 1 is 2 times 1. That's 2. So g times f of 1 is negative 6. That's all there is to it. If I asked you for h divided by g of 4, that's just h of 4 divided by g of 4. So h of 4, it's the square root of 4 minus 2. So that's the square root of 2. G of 4, that's 4 squared minus 4 times 4. So that's 16 minus 16. So g of 4 is going to be 0. Since we can't divide by 0, this does not exist. That's why I set up here that f divided by g of x, it's equal to f of x over g of x, as long as g is not 0. So since the denominator was 0 here, 4 is just not in the domain of h divided by g. So that's how we will evaluate these functions. Let me grab this right here and copy it. That way we'll still have it on screen. There we go. So again, these are my definitions. This is all part of the same example here. Now I want to say, next thing I want to do is find formulas. So I could ask, what's the formula or what's the algorithm for f plus g of x? And the way we'd get that is, well, it's just going to be the formula. If I plug x in, think of it this way. If I plug x in, I get that formula, right? So I'll plug x into f. That's 2x. Plug x into g. That's x squared minus 4x. So I'm just going to, really, long and short of it is, to get the formula for the sum, I just take the formula for each part, add them together. That's all there is to it. So combine like terms, 2x minus 4x is negative 2x. And that's the formula for f plus g. That's all there is to it. What if I wanted the formula for f minus h of x? Well, oops, f minus h of x is just going to be the same as f of x minus h of x at every point x. So I can literally take these two formulas and subtract them. It's literally going to be 2x minus root x minus 2. And if I wanted the formula for, oh geez, that's an ugly-o. Kill that, put that back. For, how about h divided by g of x? This is the other way to write division. Sometimes we'll write it with a division sign. Sometimes we'll write it as a fraction like this. So that's just, but it's the same operation. It's just going to be h of x divided by g of x. So it's going to be root x minus 2 over x squared minus 4x. And that is all there is to it. So evaluating is really pretty easy. Making formulas is really pretty easy. The only thing that's going to give us a little bit of pause, I'll save this for later. The only thing that's going to give us a little bit of pause is how to find domain of the new function. How do we find the domain of the new function? Well, we can go by example. When I had f of x was this little guy and g of x was this little guy, from our very first example at the start of the previous video, f plus g turned out to be this little guy. Remember, it was that semicircle, but moved up 6 units. But specifically, the only way I could find a point on this new semicircle is if that point existed on the old semicircle. So the domain, the lesson we learned is that the domain, of f plus g, when I ask you what's the domain of a function, a good way to think of it is to ask, what points am I not allowed to plug in? It's anything but those. If there's a point I can't plug in, it's not in the domain. Anything else is in the domain automatically. So to get f plus g, remember again the formula is f plus g of x is equal to f of x plus g of x. So to get that domain, I have to be able to evaluate f at x, and I have to be able to evaluate g at x. Well, if I can evaluate f of x, that means that x is in the domain of f. And if I can evaluate g, that means that x is in the domain of g. It turns out, if you think about the definitions, f times g of x is just f of x times g of x, etc. This work we just did, it works for f plus g, it works for f minus g, and it works for f times g. All three of those work exactly the same way. As long as I can plug the input into f and into g, I can plug it into the result of the operation. I can plug it into the new function. So let me put this in a box because this is important. Give it a little, there we go. Nice little star there. So for example, now I'm going to paste. Oh, come on. Come on. 3 fingers pinch out. How can this be so hard? Okay. Now it wants me to paste. Okay. iPad being a little bit ornery today. Let me copy this. Pew. Pew. Come on. Pew. There we go. I did it. On the new iOS, you can do 3 fingers pinching in an outward motion to paste, which is kind of needlessly complicated. And if your fingers are perpetually sweaty like mine are, then sometimes that's very difficult. So here's F, G, and H. So if I wanted the If I want the domain of f plus g of x, which remember from before, it was f plus g of x turned out to be x squared minus 2x because it was this thing plus this thing. Well, if I want the domain of that, I have to ask what's in the domain of f and what's in the domain of g. Well, the domain of f is 2x. What can I do 2x to? Any real number I can multiply by 2 and get a new real number. So the domain of f is all real numbers. How about the domain of g? I need to know each of these before I can find the domain of the new function. Well, g says take a number, square it, and subtract 4 of that number. I can follow those instructions for literally any number. I can take whatever number you give me, square it, and subtract 4 times the number you gave me. Doesn't matter what you gave me, I'll always be able to do that. And so, the domain of g is also all real numbers. So the domain of the new function, the rules are whatever point I want to plug in, it has to be in the domain of f, and it has to be in the domain of g. But that's literally any point. No matter what I pick, it's in the domain of f, because that's everything, and it's in the domain of g, because that's everything. So there are no restrictions on what number I can plug into f plus g. So that's how we find the domain of one of these. Now let's look at one where there are restrictions. How about we did f minus h of x, right? Well, again, I know that the domain of f is all real numbers. How about the domain of h? Well, we'll have to do a little work to find out. What's the domain of h? H of x is the square root of x minus 2. And the thing to remember is I can't divide by 0, and more importantly here, I can't square root a negative. I can take the 0, and I can take the square root of a positive number, but I can't take the square root of a negative number. So x minus 2 can't be negative. A way to write that in the language of algebra instead of English is to say x minus 2 either has to be bigger than 0 or equal to 0. Either one is fine. So I'll write greater than or equal to 0. And then I can add 2 to both sides and say x is greater than or equal to 2. And that's it. That's the domain. And you can see that up here. If I plug in 2, I'm going to get the square root of 0. If I plug in anything bigger than 2, I'm going to get the square root of a positive number. If I plug in anything smaller than 2, I'm going to get the square root of a negative number, which is complex, which we can't in Chapter 3. There are no complex numbers in Chapter 3. They'll show back up in Chapter 5, and that's it. That's all of them. Complex numbers are limited to Chapters 2 and 5 in this class. Okay. A way to write this in, no, you know what? X is greater than or equal to 2 is fine. I could also write it in interval notation. I could say x is in the interval starting at 2 and going up to infinity. So either one of those is fine. So then the domain of f minus h, well, how that works is whatever point I plug in, I have to be able to plug it into f. Well, no restrictions there. And I have to be able to plug it into h. So it has to be at least as big as 2. So the domain of f minus h is from 2 to infinity. Because those are the points I can plug h. And I can also plug them into f. So any of these points will go into both functions. And then I can subtract the answers and get the answer for my output. Let me do one more like this. Let's say, remember h of x was the square root of, what was it, x minus 2? Let's say k of x is the square root of 4 minus x. Nice and simple. So the domain of H was anything bigger than 2. What's the domain of K, though? Easiest way to find out is to say the number under the square root, 4 minus x, can't be negative. And if it can't be negative, then it has to be either 0 or bigger than 0. So I'll write greater than or equal to 0. That doesn't say dank, it says domain of K. I better practice my penmanship. There we go, domain of K. So if 4 minus x is greater than or equal to 0, I can add x to each side. This is why we taught you to do inequalities. 4 is greater than or equal to x. This can be 4, or it can be any number smaller than 4. So starting at negative infinity, it could be anything up to and including 4. Now, with a little practice, you'll be able to combine these two intervals in your head and say, what's the domain? But before we get to that point, we have to be able to visualize it. So let me draw a picture here. Draw 3 numbers. This one will represent the domain of H. This one will represent the domain of K. And this will represent the domain of H plus K. Let's say that's what we're, or you know what? Let's say it's H times K. We haven't done times yet. So this one's the domain of H times K. That's what we're trying to find. So the domain of H, let me line these up. Here's going to be 0. And let's say this is 2. And let's say this is 4. So H can be 2. I'll fill that in with a black circle because it can be 2. Or it can be any number bigger than 2. So I'll shade in all the numbers up to the infinity arrow. Now K, it could be 4, or it could be any number smaller than 4. So I'll shade all the numbers smaller than 4. This is kind of like that section 2.6 or 2.7 where we did multiplities. For x to go into h times k, again remember, h times k of x is equal to h of x times k of x. What that means is I have to be able to plug x into h, and I have to be able to plug it into k. Now I can't plug in any of these numbers into h. These are out. Draw that a little neater. None of these numbers are going to work because I can't plug them into h. Just like that old graph didn't go past the edges of the semicircle, this is not going to go past the edge of h. I can't plug any of these points into h, and that means I can't plug them into h times k because the h part is missing. These numbers between 2 and 4 are great. I can plug them into both of them and then get my result. Any number bigger than 4, though, that's not going to go into k. So since I can't plug those numbers into k, I can't plug them into h times k, because evaluating h times k means you have to be able to evaluate k. So none of these numbers are going to go into h times k, and none of these numbers are going to go into h times k. Those or those. So the only numbers that go into both are the ones that start at 2 and end at 4. So the domain of h times k turns out to be these points starting at 2 and going up to 4. Let's see a graph. One moment while I pull up a graphing calculator. On share application, this one. So I said that h of x equals the square root of x minus 2. Here's h of x. And I said that k of x equals the square root of 4 minus x. So the blue graph is k of x. So these are my two square rooty guys. And then I said that my new function is going to be h times k of x. So let's say y is h of x times k of x. And that's this green curve here. So I'm only able to multiply these where they both exist, starting at 2 and going up to 4. Below 2, the red curve doesn't exist. Above 4, the blue curve doesn't exist. So I can't multiply their outputs together. But right in the middle, I'm totally allowed to multiply them, and I totally do. And there's no way that's not a perfect semicircle, is it? Oh dear. Class, I'm gonna have to think about why this is a perfect semicircle. That surprised me. Math, that's the lovely thing about math. No matter how much you understand, there's always another pattern you can find. Well, I'd better get back to the lecture, otherwise I'm going to be thinking about that for a long time. Actually, I think it's time for the end of this video. In the next part of 3.4, we'll talk about. Oh no, you know what? No, we'll stick around for a bit longer. Let me head back to here. I'll just have to ponder that some other time. Why is that a semicircle? I showed you a semicircle earlier in section 3.4. See if you can piece together why that's a semicircle. Okay, let's find the formula. H times k of x is equal to h of x times k of x, right? So it's going to be root x minus 2 times root 4 minus x. Well, I can use the square root property to actually simplify this a little. It says that the square root of a times the square root of b is the square root of a times b. So in this case, root x minus 2 times 4 minus x, yeah? And then I could simplify this even a little bit more if I wanted to FOIL. So that's going to be, first is 4x, outside is minus x squared, inside is minus 8, and last is negative 2 times negative x, that's plus 2x. And that is negative x squared plus 6x minus 8. Oh, okay, I see it. This happens to be 1 minus x minus 3 squared, which is why we get a semicircle with a radius of 1 centered at the point x is 3, y is 0. Okay, that's why that's a semicircle. I'm satisfied. My open math would probably take literally any of these 5 lines as the answer if it asked you for the formula, just by the way. Okay. That problem wasn't going to let me go until I solved it. I had to, you know? All right. Do I still have, can I still paste? Dang it. iPad not behaving again. Hey, there it goes. So once again, these were our functions that I'm using all day today. Let's say I want to find the domain of, what did I say? Oh, this is going to be a pain. H divided by G of X. So we found the formula earlier, but now we're going to try to find the domain. So the formula was root x minus 2 over x squared minus 4x. But here, I said something about this earlier. if I'm dividing by g, x has to be in the domain of h. Otherwise, I can't plug it in and make the numerator. And it has to be in the domain of g. Otherwise, I can't plug it in and make the denominator. Also, we can't divide by 0. So the denominator can't be 0. So for add, subtract, and multiply, there were just 2 rules for the domain. Here there's a third rule, though. Can't divide by 0. So, first rule, x is in the domain of h. In this case, we already found that twice. That's any number 2 or bigger. Second, x has to be in the domain of g. Well, that's actually easy here. We said before, no, it doesn't matter what number I pick. I can always plug it into g. There are no fractions and there are no square roots, so there's no restrictions. Third, g of x can't be 0. And this one's going to take a little bit of effort. That means x squared minus 4x, whatever x is. This can't be 0. Actually, very little effort. I can factor the left-hand side. I can factor out an x and get x times x minus 4. That's what can't be 0. Well, if this thing were to be 0, one of these two factors would have to be 0. That's the zero product property. So x can't be 0, and x minus 4 can't be 0, which means x can't be 4. And those are the only 2 ways that the whole thing could be 0. So as long as x is not 0, and as long as x is not 4, the denominator won't be 0, because 0 would give us 0 minus 0, 4 would give us 16 minus 16. The zero product property is telling us any other number works. So let's take a look at what we've got going here. The domain of h is any number starting at 2 and moving all the way up to infinity. The domain of g was all real numbers. But for g being not 0, we had a weird condition. Can't have 0, can't have 4, literally any other number works. So for our final answer, none of these numbers are going to work, and neither are either of these. So our final answer, well, let's see, none of these numbers are going to work. And this number, well, that's bad for 2 reasons. The 0 is bad for both reasons. Please update. There we go. And then 4 doesn't work. So the only numbers I have left are starting at 2, not including 4, not including 4 on the other side, going up to infinity. So the domain of h divided by g turns out to be this interval here. Anything at least 2, but going up to and not reaching 4. Or it could be anything bigger than 4. So I'll write union and then 4 to infinity. Those are the 2 parts of the domain when we divide. So it has to be in the domain of h, which is bigger than 2. Has to be in the domain of g. Well, that turns out to be everything. And g can't be 0, so we have to cross out 0 and 4. And that's why there's a gap at 4 here. All right. So that is the second of these 3 parts. In the third part, we're going to look at that 5th operation, function composition.